Thank you very much. So let me start off by saying that everything I'm going to talk about today is joint work with Peter McNamara at the University of Melbourne. And some version of these slides is on my webpage, and the details are in a paper posted on the archive. So let me start off with a little overview. Really the goal is I want to study the representation theory of the spin group and the pin group using diagrammatic techniques. So we saw some of these diagrammatic techniques in John's talk before lunch, and techniques like Brauer algebras, oriented Brauer algebras, but for spin and pin groups. And then one thing you can do with this is you can define interpolating categories for these groups. So I also want to do that for the spin and pin groups. So I'm going to start off very gentle. We're at the end of the conference, and maybe we're getting a little tired. So I'm going to remind you some things about the spin and pin group, some basics about the Clifford algebra, and really give you a concrete realization of the spin and pin groups, because I'll tell you exactly how we construct these two ingredients, the spin module and the vector module, which are sort of the building blocks for this way of studying the representation theory. And then I'll give a brief reminder of the Brauer category. Probably in this audience, many people know what it is, but I'll just remind you what it is. Because the spin Brauer category, which is the new thing that I'll introduce, looks quite similar to the Brauer category. We have to add in some new ingredients. Okay, so let me start off, as I promised, with some sort of basic algebraic things. So let's start off with the Clifford algebra, because everything is basically built out of the Clifford algebra. So we'll fix some finite dimensional vector space, and we'll let big N be its dimension. And then we pick a non-degenerate symmetric bilinear form on this vector space. And so we're going to be studying, for instance, the representation theory of spin N or spin V. And if you know, at least also for the orthogonal groups, these things behave differently a little bit depending on whether this N is even or odd. So it will be useful to let little n be the floor of big N over 2. So that just means that we'll write this big N as either 2n or 2n plus 1. Right? And this will allow us to split into these two cases where sometimes things behave a little bit differently. So associated to this finite dimensional vector space with a non-degenerate symmetric bilinear form, we can associate a Clifford algebra. So the Clifford algebra is we take the tensor algebra of this vector space, and then we mod out by these relations. Right? So basically this form is telling us how V and W anti-commute in our algebra. Right? So that's our Clifford algebra. Okay, so it'll be useful to have explicit presentation of this algebra. So you get such a presentation essentially by picking a basis. So you can do this in various ways. You could start off with an orthonormal basis, for instance, but that's not quite going to be the basis that presents things in the way that's most useful for us. So we're going to change bases a little bit. So within each pair, say at E1, E2, we rotate our basis a little bit. Right? So we define these psi j and psi j daggers. By the way, I'm assuming here we're working over the complex numbers. Right? So we define the psi j's and psi j daggers in this way. So just pair by pair in each two-dimensional space, we're rotating our basis a little bit. And then, of course, it's straightforward to check using the fact that the EIs are orthonormal. You can just compute how these things pair under our form. Right? So all the psi's are orthogonal to each other. All the psi daggers are orthogonal to each other. And the psi's and psi daggers are orthogonal except when the index is equal. Okay, so this will be a nice basis for us. So then you take this value of the form and you look at the definition of the Clifford algebra, and this immediately gives you the anti-commutation relations in this presentation. Right, so the psi i's anti-commute, the psi daggers anti-commute, and the psi's and the psi daggers anti-commute unless the indices are equal, in which case we get a 1 here. Right, so this is probably quite a common presentation of the Clifford algebra, I think, that physicists use, for instance. So when our big N is even, this is a complete presentation of the Clifford algebra. But when big N is odd, we're missing one vector, of course. We're missing this E subscript N, right? Because the psi I and psi daggers are span E2i, E2i plus 1. So we're missing this last one. So when N is odd, you can just check what the extra relations are for this one extra generator. So it anti-commutes with the psi's and the psi daggers, and it squares to 1. So there's a presentation of the Clifford algebra when N is odd. Okay, so we want to construct in a very important module for this Clifford algebra. Okay, so this will be the spin-Clifford module. So first let me describe it as a vector space. So we take the span of our psi daggers, so this is almost half our space, and we take the exterior powers of this subspace, right? So this is, we call S. So this is going to be the underlying vector space of our spin module. So of course, we know all about exterior powers, so this has a basis given by subsets of 1 up through n. Right? So to any subset, you just have the associated wedge of these vectors in order. Right? So we have an element for each subset. So of course, the dimension of this space is then 2 to the n. Okay? So that's as a vector space. Now we want to turn this into a module over the Clifford algebra. So let's first do that in the case where our big N is even. So then we just have these psi's and psi daggers, and I just have to tell you how they act, and it's a very natural way. So the psi daggers just act by wedging with that psi dagger, right? This is an exterior, sum of exterior powers. And then the psi's act by contraction, right? So psi I acting on xj, if I is in that subset, it removes that up to a sign. And this is the sign you need for this to be an action of the Clifford algebra. Otherwise, you get 0. Okay, so very explicit, just wedging and contracting operators. When n is odd, remember we have this one extra element, this e sub n, and I need to tell you how that acts. So when n is odd, there's in fact 2 ways to extend this to that extra generator. We pick a sign epsilon. So we use these same formulas for the psi's and psi daggers, but then the en acts on any vector by plus or minus 1, and this is the sign. Right? So here's your choice, epsilon. So there's 2 ways of extending this. So we'll call this the spin module for the Clifford algebra. Okay. So now I can tell you what the pin and spin groups are. So they're both subgroups of the group of units of the Clifford algebra. Okay, so we've got this Clifford algebra. We take the invertible elements. That's a group. Inside there, the pin group is the product of all elements that have norm 1 under this form that we fixed on V. Okay, that's the pin group. And then the spin group is the same thing, except we only take a product of an even number of elements. Okay, so that's the spin group. It's a very concrete realization of these groups. Okay, but you probably know that the pin and spin groups are double covers of the orthogonal groups and special orthogonal groups. So I should explain how you can view them as double covers. So the pin group acts on our vector space V essentially by conjugation, right? Up to a sign, so degree is the number of terms that appears here, right? So it's the k here. So you can check that this is an action, and each element preserves the form. So this gives you a map from the pin group to the orthogonal group because it gives you an action that preserves the form. And then you can check that the kernel is just plus or minus 1. Right? So you get the short exact sequence, and this shows that pin is a double cover of the orthogonal group. And then if you just restrict to spin, then this maps to SOV, and again, the kernel is still plus or minus 1, and so you see that spin is a double cover of SOV. Okay, so very concrete realization of these spaces, of these groups. Okay, so sometimes I'm going to want to consider the pin group, and sometimes I'm going to want to consider the spin group, right? Because the results are sort of cleanest to state if you split into 2 cases. And let me justify why I can do this. So when n is odd, you can check that this element, the product of all these EIs, remember this was our orthonormal basis of V, that's a central element. And pin is generated by spin and this central element. Right? So when n is odd, this is a product of an odd number of things, so it doesn't lie in spin. Right? But together with spin, it generates all of pin. And they commute. So this just means pin is the product of spin and the cyclic group of order 2. So that means there really isn't much difference between the representation theory of pin and spin. And so hopefully I'm allowed to just use spin and I'm not really losing any information. But when n is even, we're really going to want to use pin. Okay, so G of V, I'm going to define to be pin of V when n is even, and spin of V when n is odd. And it's just because the results work out cleaner that way. But you should really maybe morally think that we're studying the representation theory of pin because in this odd case, there isn't much difference between pin and spin. Right? We're sort of looking at pin. Okay, so let me restate the goals that I stated at the beginning. Now we know what this group GV is. We want to study its representation theory using diagrammatic techniques, and then maybe define interpolating categories, right? Because this group depends on this n. This n, the way we've defined things, has to be a natural number, but maybe we can define some interpolating categories for categories of modules over these things. Okay, so our building blocks for this representation theory, the things that we're going to consider to generate our category of modules, are going to be two modules. So the first is the spin module. So we defined the spin module as a module for the Clifford algebra, but the pin and spin groups sit inside the Clifford algebra, right? They're subgroups of the group of units, right? So we just restrict, and that tells us what the spin module is. So we already know what that is. And then the other important one is the vector module. So we can view this vector space V that everything was built from as a module over pin by conjugation. This is almost the thing we saw before, except I don't have this sign here when I was describing this short exact sequence. It turns out a bit better for what I'm going to do next to not include that sign here. Okay? So this is the vector module. So we have the spin module and the vector module, and these are going to be our building blocks for this category, our generators. Because the important thing is that all simple finite dimensional GV modules, or you can think of pin modules, are summands of tensor powers of S. So in fact, you might think, well, I only need the spin module as my generator. And in theory, that's true, but you get a much nicer presentation of the category, it turns out, if you throw them both in. Okay, so that's why we're going to consider both of these. Okay, so there's a little bit of extra structure we're going to need to build our category. So we want to define a bilinear form on S. This is going to allow us to show that our category is rigid. So we have a bilinear form on the spin module that's defined in this way. So it looks kind of crazy because of this expression, but all it is it's saying if you pair xi and xj, you get plus or minus 1 if they're the complements of each other, and 0 otherwise. Right, and that's just the sign that you need in order for it to be GV invariant. Okay, so the important thing about this form is that it's invariant under the action of the group. So that means that it yields a homomorphism of GV modules from S tensor S to the trivial module. In particular, S is self-dual. Right? So that's the importance here. We have this bilinear form that tells us that S is self-dual. And then it's nice to know about the symmetry of this. This form is either symmetric or skew-symmetric, depending on what your n is. And there's the precise sign that appears. And if you play around with these signs a bit, you realize this only depends on capital N mod 4. Right? So, but it's more than just mod 2. So mod 4 tells you whether this form is symmetric or skew-symmetric. Okay, so I'm going to be drawing things with string diagrams. We saw string diagrams in John's talk, so I'm just going to give you my one-slide summary of the conventions that I'll use for string diagrams. So we'll be working in a strict monoidal category, and if we have a morphism from A to B, the convention will be that the domain is at the bottom, and the codomain is at the top, and then we've got some sort of picture, a coupon in the middle that represents our morphism. And our composition is vertical stacking of diagrams. And because we're reading bottom to top, so if I put F above G, that's F composed with G. And our tensor product is horizontal juxtaposition of diagrams. Right? So it's the exact same conventions that John was using. Sometimes he was in a 2 category, but it's the same flavor. Okay, so let me remind you, before I tell you about the new category, the spin-Brauer category, let me remind you of the more classical thing, the Brauer category. Okay, so we'll fix some n. I'm deliberately using the same symbol as before, even though now I'll allow it to be a complex number, because really, morally, you should think of this n as being the dimension of this vector representation. So we can define a Brauer category corresponding to that parameter. So it's a strict linear monoidal category, and I'll give it as a presentation. So we've got one generating object B. So all the objects in this category are just tensor powers of this generating object B. And then all the morphisms are built out of just 3 pieces. So we've got cups, caps, and crossings. So the cup goes from the unit object, because there are no strands at the bottom. So it goes from the unit object to 2 copies of this generating object. The cap goes the other way, 2 copies to the unit. And then the crossing goes from b squared to b squared. So all the morphisms are built out of this via tensor product and composition. So we can stack these on top of each other. We can place them beside each other horizontally. And we always have an identity, which is a straight strand. And we have all diagrams that we can build up out of these pieces. But then we impose some relations. So these are relations we've seen before, for instance, or similar ones at least in John's talk. So we have the first 2 relations that are just the relations in the symmetric group. These ones together with this crossing sliding over a cap tell us that our category is symmetric monoidal. We've got these zigzag or yanking relations that tell us that our that tell us that these give adjunctions, that give us rigidity, right? That's the word I was looking for. And then we've got this de-looping relation, and then we've got this relation where the bubble is equal to n. That's where we see the parameter. And of course, in this diagrammatic calculus, the bubble is always a categorical dimension of whatever that object was. So this is telling us that our generating object has categorical dimension n. And in the abstract language of a strict monoidal category, that doesn't have to be a natural number. That can be any element in your ground ring. So that's why I allow n to be any complex number. Or you could do it over more general rings if you want. So that's the Brauer category. It wasn't initially defined that way. So an arbitrary morphism is some linear combination of Brauer diagrams, things you built up out of crossings, caps, and cups. So here's an example of a Brauer diagram. You read the domain just by counting how many strands there are at the bottom, and you read the codomain by reading how many strands there are at the top. And the composition is just vertical gluing of diagrams, but every time you get a closed component, you can remove it at a cost of a factor of n. And then the tensor product is horizontal juxtaposition. And these came first, and in fact, they even came first in the case where you have endomorphism algebras, the same number of strands at the top and the bottom. These are Brauer algebras. These came first when people wanted to do the orthogonal and symplectic analogues of Schur-Weyl duality. And it was the Brauer algebras that replaced the group algebra of the symmetric group. And then later on, people realized there's no reason we have to have the same number of strands at the top and bottom, and you have this bigger category, and you can give a presentation. Okay, this category has a universal property. So anytime you have a linear symmetric monoidal category that has a self-dual object, so called V, of dimension n, and here I mean categorical dimension, but if it was some category of modules, then that's the actual dimension. Then there's a linear monoidal functor from the Brauer category to that category that takes the generating object of the Brauer category to this V, right? So it's the free symmetric monoidal category on a symmetrically self-dual object. Right. So let's give a concrete example of this. What's an example of a linear symmetric monoidal category that has a self-dual object? Well, you could take modules for the orthogonal group, right? Because by definition, the orthogonal group is the group that preserves a form. That form gives you your self-duality for that natural module, right? So it follows from this universal property that we have this functor, and it sends the generating object to the natural module for ON. And you can be very explicit and say exactly where all these generating morphisms go. So the crossing, as usual, just goes to the tensor flip. Your cap goes to the pairing that was used to define the orthogonal group. And then the cup goes to the dual of this pairing, and by that I mean it sends 1 to a sum of over V in an orthonormal basis of V tensor V. Again, we saw some maps like this in John's talk. So you could say very explicitly, and then any Brauer diagram, you can say what it does by just decomposing it into these pieces. And in fact, you can do more general. You can also go to, when n is negative, you can go to symplectic. And in general, you can go to orthosymplectic. So this is a more general thing. But I sort of won't mention much about super in this talk. So what are some properties of this functor? So I call this the incarnation functor. So one of the most important properties is that it's full. And again, this generalizes something that was proven earlier. So the fact that it's full, if you look at just endomorphism algebras, that means it sends this Brauer algebra, which were the endomorphism algebras in the Brauer category, to endomorphisms of tensor powers of the natural module of ON. This should be B capital N and O capital N. So that's the thing that came first, that this is surjective. That's the analog of Schur-Weyl duality, or half of it for the orthogonal group. But it's more general. This whole functor is full, surjective on morphism spaces. And then what else can you say? Well, you realize that every finite dimensional module for the orthogonal group is a summand of some tensor power of the natural module. And what that means is, because what's in the image of this functor, you get tensor powers of the natural module. But then you play this trick, you pass to the Karoubi envelope. So we take the additive envelope first, and then we take the idempotent completion, where we add in summands for each idempotent. And this fact then tells us that our functor, after passing to Karoubi envelopes, is essentially surjective. We hit all finite dimensional modules for the orthogonal group. And you can also describe its kernel. Its kernel is a tensor ideal of negligible morphisms, which we saw this morning, a precise definition of what this is, and we've seen it in other talks, so I won't recall that. So this category, this Karoubi envelope of this Brauer category, is Deligne's interpolating category for the orthogonal group. And it's defined for any value of n, right? We only have this incarnation functor when n is an integer, but in general, we have it for the abstract category for any value of n. Okay, so what's missing? What's the new thing that we want to do? So what's missing is we're just looking at the orthogonal group, but often you want to look at its double cover, the spin group or the pin group. For instance, if you're interested in Lie algebras, the modules for the Lie algebra SOV are equivalent to modules for the spin group, not the special orthogonal group, right? So you're sort of missing some things when you only look at the orthogonal group. So remember, we have this surjective map, this double cover map from pin to the orthogonal group. So you can pull back representations along this map, and you get a functor from OV mod to pin V mod. And we have this functor from the Brauer category to OV mod. So we can compose, and we get a functor from the Brauer category to pin V mod. Right? So everything's fine. We have this functor. But the problem is it's no longer essentially surjective, right? Because we only have modules that factor through the orthogonal group. Right? We're missing the ones that don't factor through the orthogonal group. And what's missing precisely is the spin module. Right? If we could add in the spin module, then we get everything, and then we get a functor that's essentially surjective, which is what we want. So that's our goal, is we want to enlarge the Brauer category so that this corresponding incarnation functor becomes essentially surjective. And we do this by going back to our abstract diagrammatic category and adding in a generator that formally corresponds to the spin module. Okay, so here's the category. So it depends on 3 parameters now. We have these 2 elements of our field, which you should think of as the analogues of n before, because now we're going to have 2 generators. So these are the categorical dimensions of those 2 generating objects.
So can you say it again, what the assumption on the field was?
On this D? The field. For the definition of the category, it works over any commutative ring. That's, well, I'm going to state it for complex numbers. Okay, so we fixed 2 parameters, which are going to be our categorical dimensions, and we need this sign. This sign comes from the fact that, remember I said sometimes we have this form that's skew symmetric, sometimes it's symmetric, and sometimes the vector lives inside the symmetric power of the spin, and sometimes it's in the exterior power, so things different happen, and that's where we have to have this sign that comes in. So according to these parameters, we define a Brauer category. So it's, again, a strict linear monoidal category that we'll define via presentation. So now we have 2 generating objects, S and V. So you should think of these as our categorical analogues of the spin module and the vector module. But now we need to improve our notation so we can distinguish between the 2. So black lines will be the spin module, our categorical spin, and dashed blue lines will be our vector module. So what are our generating morphisms? So you should think of, we sort of have 2 copies of the Brauer category, and they interact in a certain way. Okay, so we've got caps and cups of both flavors that do the same thing that they did before, but now with the V and the S instead of this thing we called B before. We have all flavors of crossings because we want our category to be symmetric monoidal. So it gives us 4 different crossings. And then the way they interact is we have this trivalent vertex. Right? So we have a vertex that goes from V tensor S to S. And that's going to be sort of the only way that these lines interact. So all our pictures are going to be built out of these ones by stacking them on top of each other and putting them beside each other horizontally. So here are our defining relations. So at the top, I wrote some dashed red lines because these are things that hold for either the blue or the black strands, right? Or mixed. You know, we have the braid relation when 2 of them are black and 1 of them is blue, etc. All possible combinations. Okay, so these are exactly the relations in the Brauer category. We just have them for all possible colorings.
So K to appear is the sign for.
We do have a kappa right there. It does not appear here. You might think it appears here, but I rescale it to make it appear there. You sort of have a choice of where it appears. It's whether I send that crossing to actually the flip or minus the flip. Yeah. And then we have some relations. This trivalent vertex should slide through other strands. That's just because we want our category to be symmetric monoidal, so the crossing should be natural. Everything should slide through strands. We have this trivalent vertex that we can sort of turn around in both ways, and those turn out to be equal. And this is nice. It makes our category pivotal, right? And then this is the only place this kappa appears. If we take our trivalent vertex and we swap 2 of the legs, we see this sign. Okay? And then we've got this relation how we can slide one trivalent vertex past another. This essentially comes from our relation that defined the Clifford algebra. You should think of this as the anti-commutation relation in the Clifford algebra. And then we have our categorical dimension statement. So the categorical dimension of our categorical vector representation is little d, and the categorical spin representation is big D. Okay, so that's our category.
So the point is that big D is 2 to the little d over 2, right? But these are algebraically independent, so you have to make them separate parameters.
That's right, that's right. Yeah, exactly. So when we want to prove certain statements, we use the fact that these are algebraically independent. You can take n to infinity, and you can prove things are linearly independent. So you can play this trick that we saw in John's talk a bit too. You can start rotating diagrams around. So we can define a trivalent vertex for any orientation just by taking the one that was our generator and rotating it. And because of this one relation about one rotation being equal to the other, it doesn't matter which way you rotate them, you get the same thing. So we have isotopy invariance for our diagrams, and so things behave very nicely. And you can show other things like this kappa appeared when we crossed 2 strands. It turns out the same kappa appears when you cross any 2 strands of the trivalent vertex, right? This is one of the reasons that's where we put the sign. It made this sort of cleaner here. And you can show things like if you have a black strand with a little blue bump on it, then this just gives you a factor of little d. And lots of other relations you can show just starting from when you start playing around with the defining relations.
So those relations that from what you just said, these are all deduced from the earlier relations.
That's right. These are the defining relations. That's everything you need. And then these are ones you deduce from those other ones. Yeah. The nice thing about giving a small presentation as possible is when you want to define a functor, there's fewer things to check. Okay, so now I want to relate this to the representation theory of the pin group and the spin group. So I want a version of this incarnation functor that we had before for the orthogonal group, but now for the pin or spin group. So let me remind you of our setup. We had an inner product space, V, with some pairing of finite dimension big N. And then we defined our little n in this way, so that big N was either 2n or 2n plus 1. And remember, I hopefully, or at least I tried to convince you that it was fine to split into these 2 cases. So this g of v is either pin or spin, depending on if n is even or odd.
So one reason to do this is that S will always be irreducible if you do this, right?
That's right. That's right. That's one of the key reasons why we do this. Okay, so we're going to be interested, we're going to relate the Sprint-Bauer category to representation theory. Of course, there's only certain values of the parameters where it's related to representation theory, right? So for the Brauer category, it was when that capital N was a natural number. But here are the parameters for our spin Brauer. So for this n being the dimension of v, that's our little d. Our big D is 2 to the little n, because that was the dimension of the spin representation, except sometimes it's a sign. Things can have negative categorical dimension, like for the symplectic group they do. And then kappa n turns out to be minus 1 to the little n big N. And again, that depends on big N mod 4. All right, so you see this sign appearing in that way. And this sigma n, if you remember, this was the describe the symmetry of this form. So when that's +1, the form on this was symmetric, and it was -1, it was skew symmetric. So it's the same sigma n that we're seeing there. Okay, so we're going to define our functor. I want to build up the pieces to tell you what all the generating morphisms get sent to. Okay, so let's fix a basis of S, and then we'll pick a left dual basis with respect to this form. And then it's important that I say left dual, because this form might be skew symmetric, so left and right dual can differ by a sign, so I pick left dual. So there's our definition of left dual, that the dual appears on the left of the form. And then we do the same thing for V. We pick a basis of V and a left dual basis. Here our form was symmetric, so it didn't matter so much, but I'll say left. And then we have these morphisms that we saw in John's talk. So we have a morphism from the trivial module to 2 copies of spin that just takes a scalar to that multiple of this, where we sum over x tensor x check as x goes over our basis. And then this exact same type of module for V, where we just are now summing over a basis of V. Okay? And you can show that these are GV module homomorphisms. You should think of them essentially as being sort of the duals of the pairings, essentially. And then the one new ingredient, really, is the thing that's going to correspond to our trivalent vertex. So the thing that's going to correspond to the trivalent vertex should be a map from vector tensor spin to spin, and it's just Clifford multiplication. Okay? So that's sort of the key new thing. These are just analogues of the maps that we saw for the caps and cups in the Brauer case. And the real new thing is the trivalent vertex, this tau here. Okay, so now we have our incarnation functor. So what is our functor? There's a unique monoidal functor from the spin Brauer category at these special values of the parameter to modules for GV, which was either pin or spin, depending on the parity of the dimension of V. It sends our categorical spin module to the real spin module. It sends the categorical vector module to the real vector module. And on morphisms, it sends our caps to the pairings that we had on these modules. It sends the trivalent vertex to this Clifford multiplication map that I told you about on the previous slide. And it sends the crossings to flips, up to a sign. So we put this sign in here so that we always have that relation, the d-looping without a sign. I hid it in here. And that's enough to uniquely describe the functor. And then it turns out that the cup and cap get sent to those other maps that I described, which I said were the duals of the forms. But that follows from this. So we call this the incarnation functor. Right? So you should think of it as an analog of this incarnation functor we had for the Brauer category. If you look individually at the blue and black lines, it's essentially the same functor. And then we have this tau that gives us this new ingredient, the trivalent vertex.
But this category doesn't have finite length, right? So, like S tensor S has infinite length. It's the sum of all exterior powers.
That's right, and the limit as n gets big. That's right, yeah, that's right. Yeah, so for this category, yeah, so in this category, if you look at, right, you take 2 black strands, which is S tensor S, and you can just draw these blue barbells across it. And you can have as many as you want, and generically, they are all algebraically independent. So you have infinite dimensional endomorphism algebra. Yeah.
Linearly independent. Yeah?
Maybe even linearly independent. Yeah, that's right. The barbell is algebraically dependent. These powers are probably linearly independent. Yeah, I think so. Okay, so what are the nice properties of this functor? It's full, just like we had for the Brauer category. After you pass to the Karoubi envelope, it's essentially surjective. This is just the fact that I mentioned before that any finite dimensional module for pin or spin is inside some tensor power of spin. And since we have spin and we pass to the Karoubi envelope, we get all sum n, so we get everything. When n is even, the kernel is a tensor ideal of negligible morphisms, so just like we had for the Brauer case. And so, by definition, when you quotient out by negligible morphisms, that's a semi-simplification. So another way of saying the same thing is that modules for this group are equivalent to the semi-simplification of the spin Brauer category, same as the statement we had for the usual Brauer category. When n is odd, this remains true if we impose one additional relation. And I'll tell you in a little bit what that one additional relation was. It was one of the more mysterious things that we came across that we were stuck on for a bit and then finally worked it out. And let me just as a side note say there are other possible incarnation functors. You can go, instead of to GV mod, you can go to modules for the product of GV and OSP M2K. You still send the categorical vector module to the vector module for GV, but you send the spin to the spin module for GV, tensor, the natural module for this orthosymplectic supermodule. And this is useful for certain arguments because it allows you to evaluate at even more generic values of the parameters.
But you know all incarnation functors? This is a class.
You're asking, are these all the incarnation? I don't know the answer to that.
But this functor is not full, right?
That's a good question. Is this functor full, she asked. Yeah, probably not. Okay, so I said when n is odd, we need an extra relation. So let me motivate, I could just give you the relation, but let me motivate where it comes from because it'll probably seem quite serious, or not serious, but mysterious if I don't tell you where it came from. So when we're in the case where big N is even, so that's type D little n, and so remember our V was big N dimensional. So if you take all the exterior powers, these are all of them, after that they're 0. And they're pairwise non-isomorphic pin modules. They're not, some of them are isomorphic as spin modules. For instance, this last one is one-dimensional. The first one's the trivial. But the last one is not the trivial module as a pin module. It's trivial as a spin module. This is one of the reasons it's important that we use spin instead of pin. But when you're in the case where big N is odd, so that's type Bn, then in fact these pair up. So the kth exterior power is isomorphic to the n minus kth exterior power, even as pin modules. Okay? So in particular, if you take this highest exterior power, that is the trivial module. So that's where they behave quite differently, right? This higher exterior power.
So I'm confused. Why n is even? I thought that then the additional element of pin will act by 1 on it, no? Wedge n.
That's right.
So why is it non-trivial?
But it acts as 1 on the other one. Sorry, you're looking at this case?
No, the above, the DGN case.
The DN case, yeah. Yeah, they're both trivial as pin modules.
But it says.
Oh, sorry. I said it the other way. These are not. Yeah, the extra element acts as -1
Minus identity. Yes.
On wedge n.
on wedge n. That's what differentiates them.
We are both trivial as spin modules.
That's right. And remember, this is the case where pin is just spin tensor, the cyclic group of order 2. And on this top exterior power, you have the non-trivial, you have the sign representation of the cyclic group of order 2. But when n is odd, then they're isomorphic. The problem is that diagrammatically, we don't seem to have a diagram that gives this isomorphism. Right? Or at least we can't come up with one. We couldn't write one down. So we don't have some diagrammatic realization. This is something that holds in the module category. So certainly there's, it's somehow sitting in the kernel. But turns out we want to impose it in the diagrammatic category as well. I'll tell you why in a second. But let me tell you what the relation is first. So here's the relation. So first of all, we can define anti-symmetrizers. If we look at just blue strands, these have the symmetric group relations. So you have a copy of the group algebra, the symmetric group there, just interpreting a simple transposition as a crossing of strands. So for any k, I can define this anti-symmetrizer, where we take an alternating sum of all the crossings. So it's the sign of a transposition times, or the sign of a permutation times the permutation realized in terms of these diagrams.
So that picture means you've got k blue strands.
Yeah, right. Yeah, so
parallel and
this,
crossing in all possible ways.
right, this K here means I've got K strands actually here. So for example, if that K is 3, this is what that is. That's the anti-symmetrizer on 3. Sometimes for anti-symmetrizer, you might want to divide by 1 over K factorial, but if you write it this way, you don't have to assume that K factorial is invertible. So I'll just use this one. But if it is, if you're in the complex numbers, for instance, then 1 over K factorial times this anti-symmetrizer, that's an idempotent now. And when you pass to the Kruby envelope, that idempotent precisely corresponds to this exterior power. Okay? So we see this anti-symmetrizer there, and after we pass the idempotent completion, you should think that that's a copy of this exterior power. Okay? Okay, so now let's suppose we're in this case where n is odd. So we have this isomorphism, right? This highest exterior power is isomorphic to the trivial module, so we want to enforce that in the diagrammatic category. So it turns out this is what we want. So if you look at this left-hand side, on the bottom we've got this anti-symmetrizer. So you should think of this as a map whose domain is the anti-symmetrizer, or is the exterior power, or the top exterior power. And then it goes to the trivial, and then it goes back to the top exterior power. So it's a map from exterior to trivial back to exterior. And then I make it some multiple of the identity on the exterior. So I'm just forcing these things to be isomorphic in the diagrammatic category. And that's just the factor that you need in order for this to be the right map. And why do I really want to impose that in the diagrammatic category? It's because one of the things you really would like to have for these diagrammatic categories is that you can evaluate all closed diagrams. Anytime you have a closed diagram, you can use your rules and evaluate it to a scalar multiple of the empty diagram. That's what you need, for instance, to know that the kernel of your map is negligible morphisms. And when n was odd, we just couldn't do that. There were diagrams that we could write down, and we just had no idea how to simplify them. So it's possible that you still can, and you don't need this relation, and there was just a trick we didn't see. But once we impose this relation, which we know holds in the module category, then we could evaluate all closed diagrams in the case where n is odd.
So how, if d is not an integer, will you put gamma function? For factorial.
Oh, no, well, it's the number of strands. So this relation only makes sense when d is a positive integer.
But your d was a
We only ever impose this relation when d is an odd integer.
Yes.
When d is not an odd integer, we don't need it. We can always evaluate closed diagrams. We have this little trick. But when d is an odd integer, both sides of this trick become 0, and we just can't, the trick doesn't go through. So you need this extra relation.
Do you need capital D to be expressed in terms of small d for this relation, or capital D can be anything?
Capital D can be anything, yeah. Okay, right, and so this relation is respected by the incarnation functor, and then all the statements I said before are true. The kernel is negligible morphism, so the semi-simplification is the category of modules, etc. So I want to say, talk about one last thing, which is an affine version of this. So there are affine versions of the Brauer category. I didn't tell you about them, but maybe some of you know about them. There's an oriented Brauer category that also has an affine version. And we saw these sort of affine flavor things in John's talk. He had these dots, which are sort of the analogues of the dots that I define here. So the affine version of the spin Brauer category, again, you have the same three parameters. We take the spin Brauer category, the same presentation I gave before, but we add on 2 more generating morphisms, which are these dots that can sit on these strands. Okay? And then here are the relations that we impose. So if you look at this one, it's quite similar to the relation we saw in John's talk. A dot slides through, and you pick up some linear combination of cap and cup and identity. And that one's quite similar. These ones are quite different. These ones look very different than they do in the affine Brauer category. But you play around with it a little bit, and you look, well, I mean, the way you come up with these relations is I'm about to define a certain functor, and you play around in the modules, and you see what the relations are down there, and those tell you what they should be upstairs. So these are all various types of dot slide, and you see the kappa appears here as well. And then these dots, when they slide over caps, you pick up a minus sign, and then when they slide through a trivalent vertex, it splits into 2 dots like this. Right, so these are the relations. So what do we do with this affine category? We have an affine incarnation functor.
in these relations, are these coefficients somehow related to, for instance, the two in Clifford relation?
Yeah, and you can rescale things. We played around a little bit. You can move these twos from here down to here, etc. But yeah, they appear because various powers of 2 appear like in the Clifford relation, etc. And you can always rescale the trivalent vertex, and you can use that to move some of these coefficients around. So we have an affine incarnation functor. So the Sprint-Brauer category went to this category of GV modules. So the general philosophy is that the affine one goes to the category of endofunctors of that category. So now this S, instead of going to the actual module, spin module S, it goes to the functor of tensorine by S, it's translation functor. And V goes to the functor of tensorine by V. So then the dots, which were endomorphisms of S and V, get sent to natural endomorphisms of these functors. So what are those? They're similar to the type of things that appeared in affine Brauer and affine-oriented Brauer. They're multiplication by something related to the Casimir element. So you've got this Casimir element in the universal enveloping algebra of SOV. You've got the usual co-multiplication. And so you take delta of C minus 1 tensor C, right? And that acts on these two factors, and that gives you your natural transformation that corresponds to the dot. And one thing that you get out of this affine, so you're studying translation functors, which are a tool that's been used a lot in representation theory. And one thing you get for free out of this setup is if you look at closed diagrams in this affine category, so that's endomorphisms of the unit object. When you're not in the affine category, I said you can always evaluate closed diagrams. But in the affine category, that's not true. You get these sort of bubbles with dots on them that don't evaluate. So you get this complicated sort of bubble algebra here. This maps to endomorphisms of the identity functor. And this affine incarnation functor you can also do where you replace the group by the Lie algebra. And then endomorphisms of the identity functor you can naturally identify with the center of the universal enveloping algebra. So you get a map from this bubble algebra to the center of the universal enveloping algebra. And we can describe exactly what the image of that algebra homomorphism is. It's the GV invariance in this center.
So actually you can think about a module. So there is a vertical string which is straight.
That's right.
And on this string you have a module, not necessarily integrable actually.
That's
yes?
right, that's right.
Just a module over the Lie algebra. And then you have functors of tensoring it with things. And the center acts in this module.
That's right, yeah.
A question about, I see a double-headed arrow, but then you're saying the image is these GV invariants, so I'm missing something.
Oh, yeah, that should not be a double-headed arrow, sorry. Our original conjecture was that was surjective. That's probably where that typo is from. And you realize you need GV invariance.
It's almost everything. Yes? So
Sorry?
it's almost everything.
That's right. In one of the cases, even or odd, it is everything. I forget which one. You don't need the GV, but in the other case, you do.
What is GV?
That's the group, either spin or pin.
It's just disconnected and because it removes some.
Yes.
There's a way of describing this as like symmetric polynomials in squares of these variables xi. Okay, so what are some future directions? What are some things that we haven't done but would like to do? It's always nice to get a basis theorem for these types of categories, explicit basis of all the morphism spaces. It's a little bit harder here because this trivalent vertices, it's not quite clear what a normal form you should have for these diagrams, like it is for Brauer diagrams and oriented Brauer diagrams. So that would be nice. The kernel, in some sense, we have a description of the kernel. We know it's the tensor ideal of negligible morphisms, but it'd be nice to give an explicit generator for this tensor ideal. So you can do this for the Brauer categories, generated by one element. It'd be nice to do a similar thing. And then there should be a quantum version of everything. So there's a Kaufman-Skane category, which is a quantum version of the Brauer category, where your endomorphism algebras, instead of being Brauer algebras, are now BMW algebras. And there's a natural functor to modules over the quantized enveloping algebra. But again, we're doing sort of the orthogonal version here. So this functor, not essentially surjective is what I meant to say there. It misses, there's a quantum version of the spin module that it misses, right? So there should exist some quantum version of this spin Brauer category that should be sort of like a spin Kaufman-Skane category that should complete this picture and add in this missing ingredient, the quantum version of the spin module. Okay, so I'll stop there. Thank you.